Now we will see how we can make this recursive solution into a DP solution, right? So this approach will be valid for all problems wherever you are able to use recursion and you have overlapping subproblems. You can convert them into a DP solution, right? So the idea is that we want to basically store the overlapping subproblems, right? So what we will do, we will maintain a array to store the solution for overlapping subproblems, right? So it basically means you are adding some memory to your recursive solution, right? So now the recursion knows what states have been computed, right? Okay, so basically this is recursion plus memoization, right? Which means you are adding some memory to your recursive solution, right? So let us see what is this concept of adding memory. So let's say, okay, I have a DP array. Let's say maximum n is 100, and let's say this is initialized with all zeros, right? So what I can do, I can pass this DP array to this function, and in this function I can accept the DP array. And now what we are going to do, now here in the recursive case, we are actually computing fib of n, right? So we are computing what is fib of n. That is not known to us, but it might be possible when we are on a given call, we have already computed fib of n, right? So whenever we compute some value, we are going to store it in dp of n. So I can say if dp of n is not 0, which means that value has already been computed in some other call. So I can just say, okay, return dp of n. So this is nothing but the lookup. And whenever you're going to compute some value, you're going to store in dp of n. So these are the two steps that you need to add to make a recursive solution as a top-down DP solution, right? So now let us dry run this code and see what happens if you compute fib of 5. Let me see. Okay, I have a DP array like this: 0, 1, 2, 3, 4 and 5, and in the beginning everything is going to be 0, right? Okay, so okay, we say, okay, we are going to compute fib of 5, so you get n, so 5 makes a call on 4, and now you can see, okay, dp of 4 is not computed because it is equal to 0, right? So we make a call on fib of 3 and fib of 2. We make a call on fib of 3 and 2, and from 3 we will make a call on 2 and 1, and you can also see that 2 is also not computed, and when you make a call on 1, you hit the base case, because if n is 1, you return 1. So this will return 1, but this call will be made later on, as we saw in the last example also, right? This will also make a call on 3, but later on. So as of now, we are just going in this direction, right? So we are not going in only this direction now. So from 2, you can say, okay, fib of 2 is also 0, which means it is not computed. So you make a call on 1 and 0. So you first make a call on 1, which says, okay, because I am the base case, I'm going to return a 1. So it returns a 1 here, right? And it will make a call on 0. It is also the base case, and it returns a 0 here, right? So now what is going to happen when you're going to say, okay, I know the dp of 2 is going to be 1. So before returning, you store the answer in dp of 2 as 1. This answer is going to be stored as 1. This returns a 1 here. And from 3, you make a call on 1, and since 1 is the base case, it returns a 1, right? So remember, in the DP array, we have not updated this as 1. You can update, but since it is a base case, we are not looking the answer in the DP array, right? But you may update this answer as well, right? But it won't matter because you're first checking the base case, then you're checking dp of n. So at dp of 3, you know the answer is going to be 1 plus 1, which is 2. So you store dp of 3 as 2. So dp of 3 becomes 2. So this returns a 2 here. Now from 4, you make a call on 2, and when you are at 2, you check if dp of 2 is 0 or not. So clearly dp of 2 is non-zero, which means 2 has already been computed. Where? Here. So we have already computed 2. This directly returns a 1 here. So dp of 4 returns a 3 here, right? And now 5 will make a call on 3, and since dp of 3 is already computed and it is not 0, so you just return from this point. Instead of evaluating the tree, you directly return, right? So this returns a 2, and dp of 5 becomes 3 plus 2, 5, and 5 is stored in, right? So this approach is called a top-down dp. So this is called top-down dp, because you are going from a top of the recursion call towards the bottom, which is the smallest case, and then you are building up your solution, right? This approach is called top-down dp, or it is also called recursion plus memoization, right? So this is the memory that you have added to your function. So this is basically the memory, right? Or it's basically an array. You can also use a hash map in some cases where these values, right? So these indices are very large, right? So maybe in some problems you will see that you cannot have a very large array, but you can have a large you can store a large index in a hash map, right? Maybe in some problems we will do, right? So this approach is top-down dp. And let us also talk about the complexity, right? If we talk about the space complexity, it is going to remain same, because you can see the maximum depth of the call stack is order of n, so it is going to be O of n. And what about time, right? So clearly you can see you have evaluated n nodes here, and you have looked up values for n minus 1 nodes here, right? So it is going to be n plus n minus 1, which is again order of n. So you have significantly reduced your complexity from exponential to linear, which is a great improvement, right? So your complexity has been reduced from exponential to linear. And let us run this code just to see if it works well, right? So let me say, okay, yeah, so here we need to also pass our dp array, and here also we need to pass our dp array. Okay, so build is successful, and let us run the code now. Let me give dp of 5. You can see the answer is 5. Let me give dp of 100. Okay, so dp of 6 is going to be 6. And yeah, dp of 100 won't work because we have made an array of 100, right? Maybe you can try for dp of 12, and yes, it's 144, right? So according to the problem, you can have proper constraints and you can solve this problem, right? Okay, so in the next video we will discuss the bottom up approach, which is again going to be very simple one, right?